Welcome to Humanity in Deep Space, a planetary conversation surrounding the pros and cons, the range of interconnected issues and hard challenges facing the human future in space. We convene regularly to discuss topics and opinions, from ethics, governance, and international politics to complicated questions of health, food, art, religion, procreation, and the human condition that must be addressed as our species continues its inevitable transition to deep space. This is episode 19, The Physics of Space Exploration. Our aspirations surrounding space exploration, while ambitious and exciting, are constrained by physics. The unalterable laws of physics, from the quantum realm to those governing space-time itself, along with human physiology and psychology, are the guardrails constraining our dreams and possibilities. This webcast will explore the central aspects of what might be possible and impossible, how our science and technology will need to evolve to push further within the boundaries of these rules, and how the things that simply, at least for now, may be beyond our reach. Our guest today is Dr. Suketu Bhavsar, Professor Emeritus in Physics and Astronomy at Cal Poly Pomona. He was born and grew up in India. After graduating from IIT Mumbai, he came to the USA for graduate studies and received his PhD in astrophysics from Princeton University. He has received the Provost, Alumni, and Dean's Awards for his teaching. Our moderator is Chris Kimmel, founder of Humanity in Deep Space and co-founder of the commercial space company Space Tango.
Hello, this is Chris Kimmel with Humanity in Deep Space. These are meant to be very open-ended forums, so we encourage all of you to ask questions when you can. If you're interested, there is a place where you can ask questions. So there is a chat room, and we'll try to get to as many of those as we possibly can. So before we get going, I want to thank our sponsors, as I always do. First, let me start with Space 629. And by the way, Space 629 is really interesting. It's really built around Dr. Clint Collins, who's been a supporter, but also is one of the Blue Origin astronauts, and he's got some very interesting insights, and we hope to get him on a future website as well. And then Kentucky Science and Technology Corporation, National Stem Cell Foundation, Media Collaboratory, the Kentucky Humanities Council, Space Tango, Baird Financial, the Children's Center, the Survey Project, the Solar System Project with NASA out at NASA Ames Research Center, Higher Orbits, Interstellar, Visit Lex, and 22 Solutions. So I want to thank everybody for their sponsorships and their support, which makes these all possible and free. And we've got a really interesting, fun topic today. We're going to delve into some of the more routine questions about physics and how that affects our ability to move and survive as humans in space, but also then talking about some of the more interesting issues, perhaps about moving beyond planets into interstellar space. So I'm really happy to have an old friend of mine who I've worked with for a number of years, who is now out in California and was the head of the honors program at Cal Poly. And I'm going to ask him to introduce himself, Suketu Bhavsar.
Oh, yes. Good morning, good evening, good afternoon, as the time zone dictates for you. My name is Suketu Bhavsar, and let's see, a very quick introduction. I grew up in India, except for 3 years in Minnesota, second, third, and fourth grades, and did my undergraduate in physics and mathematics, came to graduate school, went to Princeton and did my PhD. My mentor was Richard Gott. And after a few postdocs and faculty position, I ended up in Southern California. I got involved with the honors programs about 15 years ago, so that I now mentor students from all disciplines and not just physics. But my primary love is still astrophysics, and particularly my field is cosmology. I worked a lot in the large-scale structure of the universe, which is now called the web-like structure. I would say that my student Nigel Ling and I were the first to show that it is indeed filamentary. It's obvious to the eye, but there was no quantitative measure until some statistical method showed that. So yeah, with that, I will hand it back to Chris.
All right. Thank you, Suketu. So Yeah, let's jump in initially with some of the uh, near Earth issues. Right now, obviously, humans have moved into near Earth, into orbital Earth, and have been working and living in space for a while. Obviously, humans have gone to the moon and come back, and now there's efforts to return humans again to the moon for longer stays. And obviously, there's a lot of while there's not a whole lot of, say, space-time issues involved in those kinds of missions, there are a number of ways that physics both contribute to or make life more difficult. And so I want to talk to Suketu about some of those. And obviously one that we hear, I mean, obviously is big is the whole issue of microgravity. You can't simulate gravity on Earth. You really can't. It'd be difficult to simulate gravity of any force on a planet. You might be able to do it maybe on a ship of some sort at some point. But that raises all sorts of questions about humans and our ability to do this on a long-term basis and physically. So Suketu, the whole idea that we've evolved since the beginning of time of life in a 1G environment.
Yeah, so microgravity is definitely a challenge for humans. I think we should divide challenges into two parts. The physics challenges, what is required to get off the Earth or orbit or take off for interplanetary travel, and then the human aspects. And you brought up microgravity. An orbiting space station has zero gravity, and people have stayed there for maybe at the most maybe a year. I'm not sure exactly the amount. And we just don't know what the long-term effects are, except we do know that even for that short time, the astronauts that come back have lower bone density, muscle weakness. So you have to constantly keep up the kind of things you were keeping up with just from everyday life, because we live in a 1G environment. We've evolved in a 1G environment. So is that the kind of thing that?
Yeah, that would be. Yeah, I think all of our cells have evolved within that one G environment, and I think that's one of the things. Even talking about the moon and any kind of extended stay, and then of course going to Mars, where you're looking at even an initial mission of 2.5 to 3 years. We don't really have much information at all on how our psychophysiological systems do after that kind of extended period, not only in microgravity, but deep space, which gets us back to the whole issue of another question, which is radiation and sun flares and things like that. What are some of your thoughts? And how does that affect, does it have much effect on low Earth orbit, on the moon, and on a long-term trip to Mars?
Okay. Yeah. So radiation is a big factor that would have to be addressed. We're protected on Earth from the radiation that, in our case, primarily comes from the sun, because the sun is emitting very high energy particles out into space, called solar radiation, and the Earth's magnetic field protects us, and our atmosphere protects us. So when people talk about radiation, they're talking about light particles, photons, but extremely energetic light particles like X-rays and gamma rays can really damage cells and genetic material. Then there's the radiation of just charged particles, protons, electrons, and our magnetic field traps them and deviates them so that they don't impinge upon us. The extremely high energy particles still get through, and we might be hit by a few cosmic rays, as they're called, during our lifetimes. The atmosphere stops a lot of the ultraviolet, gamma rays, and other radiation. So we live in a very protected environment, thankfully, to our atmosphere and our magnetic field. In low Earth orbit, you're still sort of protected. But if we're on the moon, for example, where the magnetic field nor the atmosphere protects you, that would be a primary concern if one were to establish a colony and live long term. how do you keep the human body from getting, radiated and dying, getting cancer, and so on.
And then obviously, and then it's the next step in our kind of nearer term goals of Mars. You've got is there a big difference in terms of radiation exposure potential between the Mars and the Moon?
Again, the Mars mission would be much longer. So
Right.
we would have to think much more uh, uh, seriously about radiation exposure, and spacecraft take that into account. And there is a radiation shield, just in the body of the spacecraft that carrying the astronauts. Um, so again, the longevity of the mission is going to really decide how much the radiation is going to affect you, because it's over time that it compounds. As we get further from the sun, the solar radiation density decreases, but it's still there. And there's always the cosmic rays. They come from, our galaxy and other galaxies. And we know they're there because they impinge the upper atmosphere. In fact, the aurora borealis we see is that radiation of, the solar radiation mostly, but any trapped particles by the Earth's magnetic field. So we actually see that it's there when we were, the aurora borealis is an example of that radiation. Yeah.
I've read about solar flares. I mean, is there any or is there any way? I mean, what can be the impact of a solar flare? And is there any way on a longer term journey to Mars to actually protect humans from those solar flares?
So if a solar flare actually hit the spacecraft, there is a potential that it could cause a lot of damage, because basically a solar flare just has a very much higher density of these charged particles. And there's always a potential for some of them to get in. I mean, as I said, there are we are impinged upon by radiation even on the surface of the Earth. It's just a matter of how much, and there are what could be called safe doses, but that just means that it's not going to have major effects statistically. So in that sense, yeah, a solar flare would be a big deal if it actually hit the spacecraft. Now, a spacecraft is a tiny thing in the volume of space. So the probability of an actual solar flare, that concentrated radiation hitting a spacecraft, might be low, but yeah, that could
But it's
obliterate.
not zero. Yeah.
Zero.
And of course, all of these things get magnified on a trip to Mars. The again, low Earth orbit, International Space Station is like 260 miles up. The Moon is 2.5, 3 days away, and Mars, as we said, at a minimum, is probably near 5 to 6 months. And since you can really only come or go every year and a half or so, 2 years, because of orbital mechanics and alignment, you're talking 3-year missions, 2.5, 3-year missions, and all of these issues we're talking about now, radiation, zero G, all those things get magnified a great deal, and it's unclear how that will actually affect us as humans. And of course, the other issue that's not too much of an issue here on Mars, I mean on the Moon or low Earth orbit, is on Mars is the communication lag that I understand, depending upon the alignment of the planets, is somewhere between 8 minutes and 20 minutes. So when you send a message at its maximum, it means that if you talk about remote health and things like that, if you send a message, it's basically 40 minutes sending it and then receiving it.
Right. Light travel time is always going to be one of the big constraining factors in communication. You can't beat the speed of light. And yeah, the Mars orbits approximately once every 2 years. So, sometimes it's in opposition, which means it's on the other side of the sun when we're on this side of the orbit. And that's, the longest time for the longest distance between Earth and Mars. And sometimes Mars is, in the same direction of the sun as we are, kind of behind us. The sun is out there and Mars is
Yeah.
but that's still going to take a good 10 to I forget exactly the distances, but yes, there's always going to be a delay of several minutes, even at its nearest. And the round trip is going to take 20 minutes, even when Mars is the nearest to us, at least.
Right.
It takes 8 1/3 minutes for light from the sun to get to us, for example. There's no way around that. And any kind of communication is electromagnetic communication,
Yeah.
and it's the speed of light.
So we had a question just pop up, talking back to the question of artificial gravity. That since artificial gravity are there limitations to that in terms of how some of the I guess the effects?
Yeah. So what Einstein
At least theoretically.
Okay. So artificial gravity. So what Einstein discovered is that actually, it's called the equivalence principle, which is that acceleration and gravity mimic each other, and you can't tell one from the other. So, for example, if you accelerate a spaceship, and the acceleration of gravity on Earth is 32 feet per second, right? So if you accelerate a spaceship at 32 feet per second, you can simulate the same effect that we feel of gravity, for example. So you can simulate, if you go twice that acceleration, you would feel a 2G force. And that's why they talk about astronauts, having to test for several G, or fighter pilots, when they accelerate these supersonic aircraft. But getting rid of gravity is more difficult, in the sense that you have to get to 0G, you have to be in free fall. If you
Right.
if you want to simulate it, say on Earth, and NASA does this. There are planes that go up and then just free fall, but it's just a few seconds that they can do it. 20 seconds or so, and you will see people floating in that space in the airplane. And there are experiments done there. The astronauts on the space station are the International Space Lab are in 0G because it's orbiting the Earth. Basically, an orbit is just a free fall. It's constantly falling towards the Earth, but it also has a horizontal velocity, so it just keeps going around as the Earth sphere falls away from it. So that's the 0G environment. On a trip to Mars, once the spacecraft accelerated and say was going at a steady speed, you would be in 0G. One way to get gravity, and it's going to be essential in interstellar travel when we talk about it, because that's going to be for much longer periods. You can spin something. We've all felt the force you feel when you're on a merry-go-round and you feel, pushed outward. Well, that's, in a way, it's simulating gravity. And any spacecraft is going to be so to just give you an idea, to get to 1G, for example, a spacecraft that's about 100 meters across, so you would probably build it in a ring, and you would rotate it at three revolutions a minute, which is not impossible. It's easy to achieve it, because once it starts spinning, it keeps spinning. Space is a vacuum, there's no friction. That would simulate a 1G field. So you can overcome the 0G aspect in long-term flight by just giving a spin to your spacecraft.
Yeah, it's my understanding that that's certainly, obviously there's a lot of thinking about that it's at least at present time it's very complicated and very expensive, because to build engineering wise to build that at this point.
Oh yeah. So as I said, you would need, say, 100-meter diameter ring, and
Right.
kind of things you see in science fiction movies, and there's a good reason they have those giant things out in space that are spinning, because what they're doing is simulating gravity. But yes, you will need a large. Otherwise, it would be spinning much faster. And but since the question of how do we deal with gravity came up, that would be the
Yeah.
only way to deal with it. To create it by spinning a spacecraft. Yeah.
All right. I want to move now to a lot of the dreams and aspirations that the human race has relative to travel beyond Mars, much deeper space travel, the deeper interplanetary travel to beyond Mars, but particularly interstellar travel and the possibilities of that. And clearly, this is where a lot of physics and space issues of space time and things come in, come into play. So, what are your Sandy? What are your when you hear about people talking about interstellar travel? What are your initial thoughts as a physicist?
Hmm. So the initial thought is just the sheer distances involved, the sheer distances. We talked about the distance to Mars as a few light minutes, right? I mean, astronomers measure distance in light travel time. It was convenient. The nearest star, Proxima Centauri, is 4.2 light years away. When we look at Proxima Centauri, the light that is entering our eyes started 4.2 years ago from that star. So light, the fastest thing that there is in the universe, to get a handle on the speed, if a beam of light could curve around the Earth, say, it would go 7.5 times around the Earth in 1 second. That's how fast light travels. Okay, at that speed, it takes 1 1/3 seconds to get to the moon. It took 3 days to get to the moon for our spacecraft. It takes 1 1/3 second. The nearest star, it takes 4.2 years. So that distance is the first thing that comes to mind. Then there are, of course, other challenges. So, in space travel, I think the main challenge, one challenge is leaving the Earth's gravity. You need boosters to get a sizable mass up from in orbit. So I think it would be a two-stage thing, first of all. We would have to construct a large spacecraft in Earth's orbit or on the moon, send maybe prefabricated parts little by little up there, because as I said, there's a minimum size that's going to be required for all kinds of reasons. And just the sheer time it's going to involve to get to the nearest star. There are 4 spacecraft that are outside the solar system right now that we have launched. So it's not impossible. Physics says it's possible to get out of the sun's gravity and head for the stars. But the Voyager, that's the furthest away, is going to take another 70,000 years at the speed it's going to get to the nearest star.
So, given that, given the extreme the extreme distances, and let's dig into that a little bit more. It's my understanding that if you mentioned Proxima Centauri being the closest, I guess, star or exoplanet, also exoplanets, being 4.2 light years, I think that translates, and correct me if I'm wrong, into something like 75,000 years given present propulsion technologies, which makes it obviously very different in terms of and then you throw in the many other topics, which we're going to get to a minute. But what are the effects? What are the possibilities of and some of them perhaps very, very, very exotic, of decreasing those times? I mean, there's different kinds of propulsion, and there's solar sails that have been mentioned, and laser sails and nuclear propulsion, et cetera. But even if those were to be developed, how much reduced time would it actually be? And where are we in terms of even thinking about something like that?
Okay, yeah. So to have a reasonable time to get to the stars, you would have to go a fraction of the speed of light.
And when you say a fraction, what would that fraction be?
Let's say we aim for 1/10 of the speed of light. Okay. At 100th the speed of light, it would still take too long, because think about it, 4 light years away, let's forget about the 0.2, 4 light years away, 100th the speed of light would take 400 years. So at 10th the speed of light, it would take 40 years. Now, there is something else that operates with this Einstein's special relativity, and Einstein, his big contribution was that time is relative. And so suppose we went at 1/10 the speed of light to get to Alpha Centauri. Instead of 4.2 years, it would take 42 years for us seeing that spacecraft leave the Earth. For the astronauts, time would be dilated at 1/10 the speed of light, not by a great amount, but enough that it would be a shorter time period. And you say, wait a minute, how does that work? Well, there is length. They would be traveling a shorter distance also from their point of view. Alpha Centauri and our Earth would seem nearer at that speed.
Yeah.
Now, these are relativistic effects.
Yeah, Suketu, I want you to back up a little bit. I want you to get into some more detail. What do we mean by time dilation? You kind of threw it, but I need a tutorial on it a little bit. So tell me about time dilation, what that actually is, and as bizarre it is that we know it's true.
So clocks tick fastest in your rest frame. So if I'm wearing a watch and it goes tick tock, tick tock, tick tock, and you are traveling in a spaceship and you zoom by me and you're wearing a watch that also ticks and I can hear it, your watch would be tick tock, from my point of view.
But not from the
Your point of view, my clock would, excuse me.
Not from the point of view of the person in travel, in transit.
No. So from the point of view of the person who travels, his clock is going at regular rate. They don't see anything change. So from their point of view, though, the distance has shortened. The amount of distance they have to travel has shortened, and so they will. It's all consistent. They will get there in that shorter time because they are traveling a shorter distance to Alpha Centauri from their frame of reference. Now, they will have to decelerate, and that's a whole nother ballpark. Deceleration, as I said, acceleration and gravity are intertwined, and clocks tick faster or slower in gravitational potentials or accelerating frames. And so that's another effect that will come into play also. So I don't know. Time dilation is the fact that clocks will tick at different rates if they're moving with respect to each other. That's maybe the most general statement. And your clock in the rest frame you're in, that's kind of maybe technical, but rest frame just means a clock that is at rest with respect to you ticks the fastest. Any moving clock ticks slower.
So and let's assume we would still, even at a tenth the speed of light, or 0.20 the speed of light, are still pretty difficult challenges. What would the time delay first? Let's say somebody going at 10% of the speed of light from here to Proxima Centauri. What would the time delay? Just rough, not exact. I don't want you to.
Right.
What would it roughly be for a human?
I'm trying to think. It might be a 1/10 the speed of light. I would have to do the calculation.
Yeah, I don't want you to do the math.
But it would be a few months. It would be a few months. With AI, we could just we can do that after this. But you can just ask, "Hey Siri, what's the time dilation at 1/10 the speed of light?" And
it'll tell you.
I found this on the web poll. What's the time dilation at 1/10 the speed of light?
I could assure use that. I got to use that in high school science.
Yeah. Now, I actually, since this has come up, I should warn you. I've tried different things that I know the answers to. So I invite everyone out there, even what we're talking about, please go and verify things for yourself. That's what got me into physics. I said, I really wonder about the cosmos. I want to know the answers, but I want to know the tools that will get me the answers. And that's why I did physics. Now, I'm not saying that everyone spend years and years of their life, but there is so much stuff out there. And I remember when I was at Princeton, John Wheeler, who, people have heard of John Wheeler, he used to say that relativity is a field that brings the nuts running out of the woodwork. There's a lot of junk out there too. So yes, I did some experiments asking Siri about things and then did the calculations, and half the time you don't get the correct answer. So I just want to kind of interject and put that in there, because you do get a lot of stuff that is incorrect, especially I noticed for relativity. Siri or even the Microsoft AI, they get confused. And what I found is they can get to the right answer, but you have to be extremely careful in asking the question. And that's where, let me turn this off, because every time I say Siri, it wakes up. Asking the right question is absolutely essential. AI will get to the right answer, but you have to be very precise with the question.
What are some of the more exotic
Right.
ideas out there that at least theoretically right now, in terms
Yeah.
of the laws of physics, aren't prohibited? It's not,
Yeah.
we may find out differently at some point. We don't know exactly how to do those. That could change that dynamic, that equation, tremendously. Some of the things we've seen, those, people who have seen Interstellar and seen some of those possibilities. But so what are some of those, and how do they mesh with what we understand about physics and the universe?
So are you asking about propulsion systems maybe that
Yeah,
would
well,
get us to
things
the
like,
speed of
yeah, I
light?
mean, well, the more exotic ideas, warp speed and
Ah,
things that shrink space, and we'll get to this, the Lorentz contraction and things like that are just really amazing from a standpoint of what they are even thinking about. But maybe go through some of those, and what, I mean, for example, let's start with, many people grew up with Star Trek, and so what is actually warp speed? How do they
what
actually
is warp
achieve that?
speed? So I mean, Star Trek never defined what warp speed is,
Right.
but it turns out that, okay, so a a physical speed limit of the universe is the speed of light. Nothing can go faster than the speed of light. But there is something that can go faster than the speed of light. A region of space can move away from another region of space faster than the speed of light. In fact, it's happening in the universe. There are distant regions of space in our universe that are moving away from us faster than the speed of light. The light from there will never reach us. Now, if you can create something like that, an empty region of space, put your spaceship in that that is the nearest I can come to understanding what they mean when they talk about warp drives. So that's one form of travel. Theoretically, it is possible to, you would need tremendous energy and yeah. Another thing is wormholes, for example. People might have heard,
Right.
because you talked about, so I'm going to grab this piece of paper here. So here's flat space. Let me just draw A and B on it. You know, you want to get from A to B, it takes some time. But suppose you curve, you warp that space so you can jump from A to B. You pinch space between these two distant things. Now, we're talking about three-dimensional space. I'm just showing it on a piece of paper. But suppose you pinch it so that A is very near B, and then you jump across that hyperspace. That's like a wormhole. So there are ways to get very far away with these exotic ways that physics does allow. But to do that, what would it take to pinch space? Tremendous energy, tremendous mass. It's probably easier to build a spaceship that tries to get to the speed of light than try to do this. But theoretically, these are some of the exotic ways you can do it. Warp drives, curving space time.
So when you let's interface that now a little bit more with time dilation. If you were able to do that, let's say that you used warp speed or you used wormhole or some other kind of exotic system, and you were to let's say you were to go to Proxima Centauri. We put a couple hundred astronauts from Earth, and they go there. How many years would have passed by the time they get there? It's 4.2 light years away. Approximately how many a year? So they're now what? They're now 4.2 years older, right? Because they're in the state of, is that correct?
Ye,
Rough?
rough, yes. So the two things come to mind. I could only show you the bending of space, but remember, we live in space-time. We live in a four-dimensional universe, at least, three of space and one of time. There might be other dimensions, but we won't even get into that here. But you're actually curving space-time. And so the astronauts might get there in 4.2 years, say. Hundreds or thousands of years may have passed on Earth because you have changed the conditions that these astronauts are traveling through in space and time. And so again, space travel, if we could achieve this, would be possible for the astronauts. But we may never live to see them actually get there because time is passing at a different rate on Earth. It's this clock's ticking at different, their clock is ticking, tick, tock, and our clock is going tick tock, tick tock, tick tock, tick tock, and hundreds of years have passed.
So really, even with exotic forms of time travel that we might be able to eventually, maybe thousands of years from now or whatever, achieve, you can't. It's really not a round trip, right? I mean, you really can't. I mean, you can come back, but everybody's going to be gone.
Everybody's going to be on. Yes, it's not a round trip. So this exotic form would make it maybe able to travel in one generation rather than multi-generational travel. But yeah.
But you couldn't come back.
But you couldn't come back. Or if you came back.
Everybody. Well, you could come back, but everybody would be dead.
It would be an Earth that you would not know.
Right.
Centuries might have passed on Earth.
Right. So, and I think when we talk about, you mentioned, you brought up this issue of multi-generational travel. I think we agree that more than likely, regardless of what kind of travel we end up using for very deep space, obviously beyond our solar system, that it's going to have to be, even approaching light speed, it's going to be multi-generational. So
yes.
talk a little bit about, I mean, I say that, but then talk a little bit about what does that mean? I mean, if you were to say, okay, we now can travel at 80% the speed of light, or 70%, or whatever it is, 10%, and what would multi-generational, and how would that actually be designed and developed? What would that look like in terms of numbers and people and diversity and all the other things?
Right. So yes, so let's say we found a propulsion system that could attain a tenth or even say 99% the speed of light. Still, this spaceship would have to be something that may not reach a destination that is habitable within a lifespan. So we're talking about now a mission that would have progeny, maybe several generations down, actually completing the trip that their forefathers started. One thing that comes to mind is just survival, enough food, enough water, but then genetic diversity of this population, because you would have to have a minimum number of astronauts on that minimum number of travelers, I guess, don't even want to call them astronauts, so that generations down, there's still a viable population that can thrive and and survive. And it's not inbred, for example. So the challenges are there are the physical challenges of attaining those speeds, which they're theoretical, fusion reaction. It won't be chemical rockets, light sails, laser sails. And then there is the human aspect of what would such a trip take on humans and how many would be needed. So if you needed at least a few hundred humans for the diversity aspect, then you would need a spacecraft that large. That means you would need propulsion that would accelerate a spacecraft that large to 0.1 or 0.01 the speed of light. And you need to protect them against radiation. There might be mutations along the way.
What would the critical mass of people, just hypothetically, for a trip to Proxima Centauri, if we wanted to do what you achieved? How many people are we talking about?
People
10,
speculate
100,
that
1,000?
at least in the hundreds, not in the tens, at least in the hundreds. Maybe a couple of hundred would provide the minimum diversity, and it would be sort of a diverse, multiracial, very diverse population of people that would probably be selected for all kinds of things, because you do not down the line, want a 10th generation that all has some kind of, disease because of a dominant gene that just took over the population.
Right. And what about, I'll throw another wrench in this discussion, and with a multi-generational voyage, which I think everybody agrees that's what we're looking at if we actually achieve this at some point. At least right now, and we may know differently in 5 years or 20 years or 1,000 years, we don't know that humans can safely reproduce in space.
That's right. Yes. Yes.
So that's another big issue. And again, it's not just, and it's not going to be easy to, it's not kind of almost, you're going to need like a longitudinal study, because it's not going to be easy, because you can't, even if somebody, you say, okay, we've had X number of people, they reproduced, they all gave birth to, quote, healthy babies, so we can do it. Yeah, but you still have to figure out what happens to them after 1 year, 2 years, 5 years, 6 years. I mean, if 20% of them die after 5 years, that's obviously an issue.
Yeah. No, we're definitely going to have to establish space colonies, say on the moon, which is the nearest, and which probably might be the simplest, maybe Mars. And then interstellar travel will probably take place from that base, because you now avoid having to escape the Earth's gravity first with that spacecraft, which is going to be impossible for such a large spacecraft. I mean, you need chemical rockets. But yes, you're right. You will have to establish multi-generational colonies within the solar system, I think, before we even venture out into interstellar space. So it's not even a trip of 3 or 5 astronauts to Mars. It's establishing an interplanetary colony before we venture out into interstellar exploration.
From an ethical standpoint, even in today's world, it seems like that talking about, there's been a lot of talk, among people, that we go to the moon, we go to Mars, first or whatever. We want to put so many, 100 people on Mars or 500. It seems to me that's a really kind of a big issue from an ethical standpoint. If we don't, it's hard to colonize any place if you can't safely reproduce, and we don't know that. So I'd be interested in any questions some of the audience might have. It seems like, how do we deal with that, not just from a technological standpoint, but an ethical standpoint?
Yeah. And of course, colonization on Earth hasn't boded well, as we know. So now here, of course, we're talking about colonizing planets and places, as far as we know, where no other life form exists. So it would just be us. But again, I can't help but think back a few centuries to, our generation and several generations after us, I think, are poised where there's there's very little left on Earth to explore. When time of Magellan and Marco Polo and Columbus and Drake and Cook, there were parts that you could kind of go and explore that at least your part of the world didn't know about. But the Earth was contained. But I was thinking, what drove all those? Except for Darwin's voyage, it seems to be economy and trying to conquer. Seems like it was material gain and religion that drove many of those expeditions. So sometimes in my more cynical moments, I ask myself, what is going to really drive us to go out there? Is it going to be the same kind of, forces? We talk about tourism, but how many of the early explorations were tourists? There were no tourists on those ships.
Yeah, I mean I think that's a very good point. There's a lot of ethical issues that are at play here, and we won't get into a lot of them. We've actually had some webcasts in the past that talked about this. But going to Mars obviously brings issues. The moon is obviously a lot closer, maybe, to test out some of these things. But I also want to now, because we're still talking about time, another issue that has always fascinated me, which I can kind of understand, but I really don't understand it. Again, that deals with time travel, is the Lorentz contraction, and how that interfaces with light speed. And can you kind of go through that? To me, that really is very, very, very strange.
Yeah. So one of the consequences of relativity is that both measurements of space, so we have a ruler that measures, say, 12 inches or 1 meter, and measurements of time. We have clocks that go, tick tock, measuring off seconds. Both those quantities, both those measures, those fundamental measures of space and time, length and interval, are relative. So you don't hear about Lorentz contraction as much as time dilation, but they're both consequences of special relativity, which is just the theory of how lengths and times measured in one frame. A frame is something where nothing else is moving with respect to you. And another frame that is moving past you, a train, for example, how length and time differ as measured by you in your frame and in that other frame. And lengths are shorter in anything that is moving past you, and times, the clocks tick slower. So a train is moving, just at the most 100 miles an hour, say. You don't see these changes. But when something is moving close to the speed of light, 1/10 of the speed of light, you start seeing these things. And so a ruler will look foreshortened in that frame. If you have a ruler in your frame and that ruler whizzes by you, it'll actually be shorter than your ruler, even though the two rulers were, say, started out the same, and somehow you got it into a moving frame. So it's simply, I mean, if you're asking how does it happen, well, you may as well ask how does time dilation happen, and it follows from the constancy of the speed of light. So I won't get into trying to understand relativity here, but the speed of light is the same for anyone that is moving, you or that person whizzing by. And if speed has to be the same, what is speed? Length over time. Then something has to give in length and time if that ratio has to be maintained constant. That kind of a hand-waving argument that doesn't write down any equations satisfy you. The speed of light is the same for me or you traveling in a spaceship.
Yeah, I mean, as I understand, Lorentz contraction is if that space contracts in the direction that the spacecraft is moving.
Yes.
At near light speed. I don't know. I mean, I can tell you that, but I don't understand how how space actually contracts. So, it may be for me sitting on Earth at rest, it's a 10-year trip, but for you, it's 1 year, because not just the speed of light, but you've also dealing with the space itself is actually contracted.
No. So it's not correct to say space is contracting. It's the measurement of length
Okay.
so it's intervals. So we're not talking about time, or we're not talking about space. We're talking about intervals between 2 points in space and intervals between 2 points in time.
Okay.
The measurement of those intervals are relative. That's what relativity says.
Okay.
The measurement. So you are measuring the length of that train cars whizzing by you, say, and you will come to a different conclusion than the person in the train. You will argue about the length of the car from front to back, and both of you are right. As measured by you, that car is going to be shorter as it's whizzing by you than as measured by the person in the car for whom the car is at rest.
I want to talk for a second in the few minutes we have left. There's been a couple of questions that came in dealing with this kind of topic. One is, if humans are on these longer missions, even if they're, not 10,000 years, but 100 years or 500 years, they're multi-generational. A couple of things. One, you've got, aside from all the physical issues like radiation, you've also got, what do they do every day? The issue I even know now, there's, even with some astronauts now, they talk about boredom occasionally.
Okay.
So you get issues of what are they going to do? What are they going to eat? All those things that make us human, that will enable us to actually we can't just survive, we have to thrive in these trips, because we have to be working as well. And so, while let's assume for a moment that humans, if we have these technologies, will eventually visit at least Mars and some of these other places. Given that, one of the persons asked, well, is it more realistic to think that really these kinds of interstellar trips may be robots and not humans, because of all the things we've just talked about?
It may be that eventually our venturing out into interstellar space is going to be the things we create mechanically and intelligently. So it'll be robots. It'll be smart robots. Maybe robots that can reproduce. Probably not. It'll have to be robots that reproduce. You can teach a robot to make itself, and so in fact, it'll they can probably survive radiation. They're not as vulnerable as our cells. So yes, I think very much so. Interstellar travel by us may eventually be through the robots we create.
Or some combination.
Yes, if you can replace a biological system with mechanical systems, or a mechanical system with biological systems, it might be a hybrid.
Yeah. Well, I think also, when you look at the difficulties and the length of time, a little bit different subject, but it also lends itself to the question of why haven't we been visited by advanced civilizations? And they have to be able to traverse interstellar time, and just knowing the length of time, et cetera. It's not certainly beyond the realm of possibility that they just haven't, we're just too far away.
Yeah.
We're just a grain of sand, and they just haven't gotten here.
Yes, what you just brought up is kind of popularly known as the Fermi paradox. Enrico Fermi, during the Manhattan Project, during the making of the atomic bomb, once at lunch is supposed to have, suddenly blurted out to colleagues he was having lunch with, other physicists, saying, "Where are they?" And what he meant is, the sheer size of the universe means it must be teeming with life and with intelligent life. Some of it must have evolved, and some must be way more advanced than us, just purely from the sheer numbers of habitable planets and so on that we know would be there. And so, wouldn't one of them have ventured out into space? Wouldn't one of them at least be colonizing the galaxy? And if so, where are they? And so maybe something once an intelligence reaches a certain stage doesn't want to do or can't do, or and so you brought up the robots. Well, why aren't even the robots here? Why on earth do we not see any sign of an alien civilization that has ventured out?
Yeah, and that's an unanswered question, but I think it's fascinating. So we just have a few minutes left, but Suketu, before I let you go, I have to ask you, by the way, Suketu and I have known each other for a while. He used to be at the University of Kentucky as an astrophysicist, and so we worked together on some things. But he told me a story once that I was amazed at, and I'm going to ask him to repeat this story about when he was a student at Princeton, and he was walking around campus or across the street and ran into someone who maybe needed help with their groceries.
Oh,
So I want you to tell that story before we go.
My claim to fame. I was standing at a traffic light.
And you were a student, right?
I was a student. I was a graduate student. I stopped at a traffic light on Nassau Street, and a elderly lady carrying a bag of groceries had also come to that traffic light. And when the light turned green, I asked her, "Can I help you with your groceries?" And she said, "Why, certainly, young man," in a very deep German accent. And as I'm carrying her groceries, she says, "What do you do here?" And I said, "I'm an astrophysicist." "Oh, I once worked for a physicist. Have you heard of Albert Einstein?" I was carrying groceries for Helen Dukes, Einstein's secretary. She was probably in her, 80s or so. My claim to fame is I carried groceries for Einstein's secretary.
And she wanted to know whether you'd heard of him.
Yes, that was her question. You might know. "Oh, I once worked for a physicist. Have you heard of Albert Einstein?" I practically dropped her bag of groceries.
All right. Well, we're out of time. I want to thank everybody for joining us today. Sorry we couldn't get to all the questions, but you can always email me at kkimmel@humanityanddeepspace.com. If you'd like Suketu's email, you want to ask him some questions. In fact, what is your email address in case people want to get it?
My email address is S as in Sam, P as in Paul, Bhavsar, my last name, BHAVSAR, @cpp.edu. But Chris, you said this also is recorded and on
Yes,
YouTube.
we will. Yes, we
Can people
record
ask
this.
questions there?
No, this will be recorded and posted on our YouTube channel.
Okay, but there's no comment section where people can ask, comment?
No, not on that
Okay.
channel. Maybe that's something.
not on that
That's a
channel.
good idea. That's something we ought to consider. But
Yeah, because I was going to say I could answer questions there as they get asked,
Yeah.
Over time even.
That's good. That's a good point. I think we should talk about that.
Okay.
We should talk about that. Okay. Well, thank you, Suketu, so much. It's really been interesting. I could, talk about this another
Always a
couple
pleasure,
hours.
and we can talk for hours.
Yeah, maybe we can do a follow-up. If people have some things that we didn't get to that are challenging their brains, please send them to me, and perhaps we'll follow up with continue this conversation, because I do think these topics are some of the more interesting kind of existential issues that we as humans face. So again, Suketu, thank you everybody for tuning in. I want to again thank our sponsors, Space 629, and then Kentucky Science and Technology Corporation, National Stem Cell Foundation, Media Collaboratory, the Kentucky Humanities Council, Space Tango, Baird Financial, the Children's Center, the Survey Project, the Solar System Project with NASA out at NASA Ames Research Center, Higher Orbits, Interstellar, Visit Lex, and 22 Solutions. Thank you very much.
Thank you for joining us for Humanity in Deep Space. In his book, Pale Blue Dot, A Vision of the Human Future in Space, Carl Sagan wrote, "Your own life, or your band's, or even your species, may be owed to a restless few, drawn by a craving they can hardly articulate or understand, to undiscovered lands and new worlds." Our continued exploration of space is accompanied by profound questions, responsibilities, and obligations. What is our place and ultimate responsibility to the larger universe? And how do we maintain a sense of humanity as we leave the planet Earth? These questions and more are discussed in our videos, as well as other curated content at www.humanityin.deepspace.com or on YouTube by joining Humanity in Deep Space. The music for this episode was written and performed by Danny Grandstaff and is available at dannygrandstaff.bandcamp.com.